In this lecture, I will discuss about the electronic properties of solids. Uh, on the basis of electronic properties of solids, one can explain number of physical phenomena related to the metals. So, how solar panel basically works, how hard disk of a personal computer works, how this microwave oven works, what is superconductivity, how magnetically levitated train runs on the train track. So there are a wide scope of this particular chapter, and especially for this particular concept that cover many number of phenomena like electric current into the conductors, light emitting diodes, how they work, photodiode, transistor, power lines. All these things basically one can explain on the basis of this particular concept. So free electron theory of solids I have to cover. That idea basically is associated with this picture where these green color balls indicate to the positive ion of the lattice of that particular metal, and these black dots indicate to the free electrons that is negatively charged, and they can move here and there within the lattice freely, right? So before we go into that particular detail of the chapter, there are some outlines to make this picture more clear, that how one can explain the electronic properties of solid on the basis of free electron theory gases. So my first question is that what are the properties of the solids? So in introduction I will discuss about it. The second question is what is free electron gas concept? Third point is how and why we use particle in a box concept on the electron gas in metals, right? So in this particular topic, the electronic properties of solids, if one have to understand that a basic concept of the quantum mechanics, that is particle in a box or particle in a infinite potential well, that information is must. Now my point is that I have described here at the second stage about the free electron gas, and then after I have implement the approach of a bound system in quantum mechanics on the free electron gas. So how and why we use particle in a box concept on the electron gas in metals, right? At the fourth point, the question is how to find out the eigenvalues and eigenfunctions for the free electrons. So here if I using the approach of particle in a box on the electron gases, then I have to find out the eigenvalues and eigenfunctions for the free electrons, right? These free electrons related to the free electron gas, and that I will discuss is in a systematic way. Number 5, what is the concept of Fermi energy? Number 6, how to find out the number of electrons, velocity and momentum of these electrons correspond to any energy level for the free electrons in a metal. At 7th point, I will discuss that how the free electrons are distributed among the available energy states. So here up to the 7th point, how I am going first of all that define the properties. At second point, the free electron gas in metal, then use a approach of free particle in a box. Then after I have find out the eigenvalues and eigenfunction of those free electrons, then define a Fermi energy level, and then after the energy, velocity and momentum, how many number of the electrons are these up to the Fermi level. So these points I have discussed. at 8th point I have discussed about the density of energy states. So if one has already find it out that these are the total numbers, so these number of electrons actually distributed into the different energies levels. So how many energy levels are those? That is basically energy density of energy states. So when one analyze the Fermi-Dirac distribution function on the basis of temperature, what results it tells about the probability of electrons in that energy states. One knows that electrons are fermions, and distribution of the electrons in particular energy states can be defined with the help of Fermi-Dirac distribution function. At this particular stage I have to discuss that on the basis of temperature, at absolute temperature T is equal to 0 and T greater than equal to 0, what happens? How the probability distribution function behaves. That analysis is discussed at the 9th stage, and then at the end how one can find out the average energy of free electrons is discussed. So these are the 10 points of this chapter, which I have discussed in a systematic way. So at the first stage यहाँ पे जो डिस्कस किया है वो डिस्कस ये किया है कि मेरे पास में कोई भी एक करंट कैरिंग कंडक्टर हो सकता है, ये सिंपलेस्ट एग्जांपल है. उस कंडक्टर के अंदर जो इलेक्ट्रॉन्स का फ्लो है, इलेक्ट्रॉन्स का फ्लो के कारण करंट है. तो ये जो इलेक्ट्रॉन्स हैं, ये जो फ्री इलेक्ट्रॉन्स हैं, इनकी नेचर क्या है और ये किसी मेटल की जो प्रॉपर्टीज़ हैं उसको किस तरह से अफेक्ट करते हैं, उन्हीं पॉइंट उन्हीं अफेक्ट्स को बेसिकली यहाँ पे स्टडी किया हुआ है. तो नंबर 1, द फर्स्ट स्लाइड ऑफ दिस पर्टिकुलर लेक्चर is related to the free electron theory, electronic properties of solids, right? So in introduction we know that solid are formed by a strong bonding between atoms, may be broadly classified as into two categories, एक metals and second non-metals. Metals are categorized further, conductors and semiconductors. Non-metals means insulator, right? So the focus is only on the metals, and metals are of two types, conductors and semiconductors. And these conductors and semiconductors are formed with the 4 type of bonding between the atoms. Number 1 is covalent bond, number 2 ionic bond, number 3 metallic bond, and number 4 van der Waals type bond is. These bond basically can be explained with some simple picture. Here I have considered, in case of number 1 covalent bond between 2 hydrogen atoms, that basically is shown like this way. In case of H2, these 2 electrons are shared by both the atoms of hydrogen atom. And in case of ionic bond, you know that sodium chloride is the simplest example, where sodium have one extra electron and chlorine have some requirement to get the stable configuration. So when sodium basically donate 1 electron to the chlorine, so as a result what happens, sodium here is a donator. So because of that sodium have a positive charge and chlorine is acceptor, and because he is accepting only 1 electron, and because of that only 1 negative sign. So this indicate Na plus Cl minus to that particular picture. Metallic bond, you can see here that in a particular metal these positive sign indicate to the ions of the metal, and negative sign indicate to the electron cloud in that metal. And there is an electrostatic attraction between these positive ions of the metal and the electron cloud. Because of that, this system is in equilibrium. And number 4, that is related to the van der Waals. So van der Waals is shown by this case. Here electron is revolving around the nucleus, that is you can say hydrogen atom, and this is their neighbor, again a hydrogen atom. So the interaction of this electron with the nucleus of the neighbor atom, so that interaction actually is very small, and that can be defined through the van der Waals attraction, right? Van der Waals attractions basically are weak interactions. So this is the idea of bonding between the atoms, how many type of the bonds are available between the you can say metals. So now the point is about the properties of the metals or metals in conductor or semiconductor. So it is important that we have to understand the behavior of electrons in metal, because electrons decide the properties of a metal. So the main of this lecture is to understand the role of electrons in deciding the properties of metals. Main properties which we know are: number 1, high electrical conductivity and the thermal conductivity. Now, what are those properties of metals for which Drude and Lorentz have been attempts on the basis of free electron theory? Electronic properties of the solids explained on the basis of free electron theory model that was proposed by the Drude and Lorentz. So here, what basically are those properties of metals, right, which Drude and Lorentz have been attempts on the basis of free electron theory? So before we go into the detail of this particular section, so we have to understand the idea first of all about the free electron. So वो free electron क्या है? Which electrons are considered free into the metal? So the example are considered here of sodium, magnesium and aluminum. You know the atomic number of those 11, 12 and 13 respectively. If you see the electronic configuration or number of electrons in their cells, so you can say that in the first cell there are 2 electrons in case of sodium, 8 into the second cell, 1 is into the third cell, and similarly for magnesium and aluminum. So 1, 2, 3 electrons are the outermost orbit electrons of these 3 atoms. So the valence electrons are responsible for the conduction of electricity, one knows, and that is basically is current. So these electrons are called conduction electrons. If I write here the electronic configuration of the sodium, so these 1s2, 2s2, 2p6, these 10 electrons basically develop a core of that sodium atom, and one is this outermost orbit electron, that is a very loosely bound with the nucleus and is valence electron also. So now the point is what basically I have defined here a core of the atom or ion and the valence electron. So if one have to define valence electron, that is defined in case of sodium, valence electron, the outermost orbit electron, this is in third cell, s is orbital, so n is equal to 3, l is equal to 0. L is the orbital quantum number, n is the principal quantum number. So what are the properties of metals for which basically Drude and Lorentz propose the idea of free electron theory of gases? So in the first slide we have seen the idea of free electron. What is the free electron? Valence electron is the free electron. And now we will discuss about the properties of metals, that what are the properties of the metals. So there are some outstanding physical properties of metals are mentioned, in which the number one is metallic conductors obey Ohm's law. It means that the current density J is directly proportional to the applied electric field E. So J is equal to sigma into E, where sigma you can say is the conductivity. This is the first properties that is related to the Ohm's law, and second one is high electrical and thermal conductivities for the metals. Number 3, at low temperature the resistivity rho is proportional to the fifth power of absolute temperature. Right. So one knows that these sigma is the conductivity, rho is represented by the resistivity, both related with this inversely proportional relationship. Right. So these were the three properties. The next property is, at the room temperature resistivity of metals is in the range of 10 raised power minus 6 to 10 raised power minus 8 ohm meter, and it increases on addition of a small amount of impurities. If resistivity will increase, it means conductivity will decrease. So resistivity normally decreases with decreasing of temperature. So this is the second statement about the resistivity. For most of the metals, next point, for most of the metal resistivity is inversely proportional to the pressure. Right. So here rho is represent to the resistivity and this P represent to the pressure. And the last point, for superconductors metal at absolute temperature the resistivity becomes 0. There are some metals basically their resistivity becomes 0 at absolute temperature. Now the G point, in the magneto-resistance effect, the conductivity of metals varies in the presence of external magnetic field, and the ratio of thermal to electrical conductivity is directly proportional to the absolute temperature. This is known as Weidmann-French law. So free electron theory model explains successfully many of these common properties of metals. This is the idea. So some of the properties are mentioned here, and with the help of free electron theory we will just try to explain some of the properties which we have discussed here. Now the next point. Now we have understand what is the free electron, what are the basic physical properties of the solids, and now the point is about the assumptions of the free electron theory model. So what is basically free electron theory? So we know that in a metal, the metal crystal have positive ions whose valence electrons are free to move between the ions. These free electrons, valence electron, are equivalent to the molecules of any gas. So here you can see this is the sodium metal. So by this picture I have just tried to show that lattice. Sodium has a BCC structure, and distance between nearest neighbors is 3.7 angstrom. Right, the distance between one atom to the second one, their neighbor, is of 3.7 angstrom. So in this picture the distance between these two atoms is of the order of 3.7 angstrom. If I write the electronic configuration of the sodium atom, that is 1s2, 2s2, 2p6, 3s1, as you have seen earlier. These electrons are distributed into the cell like this one, 2, 8 and 1. This is first cell, second cell and the third cell. The radius of the third cell, where this last electron, valence electron, exists, that is represented by R, and that is 1.9 angstrom. So there are two things I have mentioned here. One is the interatomic distance between the sodium atom, and second is the radial distance of the valence electron in the atom. Right, that picture may be more clear from this artistic view. This is my sodium atom, first sodium atom. This is second sodium atom. The distance between these two atoms, two neighbors in the sodium lattice, that is of the order of 3.7 angstrom. And the valence electron radial distance of that in an orbit of the atom, of an individual atom, is 1.9 angstrom. So you can see that there is enough space for this electron and for this electron of the second atom to move in between these two atoms, right? Because this is 3.7 angstrom और ये यहाँ पे जो आपका है इलेक्ट्रॉन वो only 1.9 एंगस्ट्रॉम रेडियल डिस्टेंस के साथ में है और दूसरा एटम इस पोजीशन पे है. सो दिस इलेक्ट्रॉन कैन मूव इन बिटवीन these two atoms of this lattice. So this was the idea. It means this electron can move in between the atoms, in between the ions. So this is the idea, main idea of the free electron theory of gases. So now the second point, the crystal is bound together by the positive ions, that is core of the atoms, and negatively charged electron gas, right, by the electrostatic force of attraction. So first point was what? These electrons can move in between to the ions, and second point is about the stability of the system. So that is because of the electrostatic force of attraction between the positive ions, core of the metal ions, and the cloud of the free electrons. Third point, the mutual repulsion between the electrons is ignored. The third assumption of the free electron theory gases is what? That the mutual interaction between these free electrons, right, that is basically is ignored. No contribution of the mutual interaction between the among the electrons. So number 4, the potential due to positive ions is uniform. So there is no charge change in energy of the electron in lattice. The fourth point basically is assumed that because of the positive ions of the metal, potential remains uniform. So there is no change into the energy of the electron in lattice, right? In the lattice, the potential energy is constant, and because of that, when electron moves in between those ions, the electron does not change their energy, right? So potential is constant, or you can say on the other hand that is equal to 0 inside the metal. Number 5th point, the electrons are moving in random directions and collide frequently with the residual ions. The 5th point basically, these electrons are moving in random direction collide frequently with the residual ions. Residual ions, here I have considered the case of sodium ion. So the core of the sodium ion is the residual ion, except to the valence electron. Rest of the part of the atom is known as residual ions. Here it is assumed that valence electrons travel in constant potential inside the metal. These electrons are prevented from leaving the crystal because of the higher potential at the surface of the crystal. So electron is treated like a particle in a well as an infinite depth well. I defined here that the assumptions about the free electron gas concept in earlier slides, that why we are treated those electrons which moves in between the crystal lattice are free, right? Because there is no potential inside the metal. And second point, we are saying that these electron cannot escape automatically from the surface of the crystal. So it means at the surfaces of the metal is higher potential. On the other hand, one can say that potential is infinite. So electron cannot jumps from the or leave the crystal surface. So electron is treated like a particle in a well, right? That is in an infinite depth well. I am making this statement more clear for the free electron theory of gases, right? Because we have to apply here a free particle in a box approach on the free electron gases in metal. So what are the restrictions, what are the boundary conditions actually for that concept? So here only 2 points we have discussed. Number 1, assumptions for the free electron gas, and second, about the potential inside the metal. So the idea is like this one: a particle is in a box or in infinite potential well, depth well. The dimension is considered here x is equal to 0 to x is equal to L. Potential is equal to 0 inside and infinite at the boundary. So electron in a one-dimensional potential well.